let's consider how we can use our calculus knowledge to help us solve kinematics problems. And in this video, let's just consider free fall motion, which means that it's only in the vertical direction, and the only acceleration is acceleration due to Earth's gravitational field. So first thing we need to do is go and, our usual, put our reference frame here. So we'll say, in this case, positive y is positive in the up direction. Now we have our equation here that's our standard position time equation. So it says the change in y is equal to the initial velocity, and since we're only considering free fall, this is in the y direction, initial velocity times time plus 1/2 acceleration, and again this is acceleration in the y direction, times the square of time. So our situation that we're considering here is pretty typical. Just a ball is dropped or a rock is dropped straight off a cliff and it just falls straight down, and we know that this height between the cliff and the ground is our delta y. So the next thing we might want to just remind ourselves is that delta y can be expressed in a variety of ways. For example, it can be y final minus y initial is equal to v initial t plus 1/2 at squared. It could also be expressed y final is equal to y initial plus v initial t plus 1/2 at squared. Now the reason for all these variations is just it depends on the wording of the problem. You can see from this step to this step, all I did algebraically was add y initial to both sides of the equation, which removes it from the left hand side and puts it on the right hand side. So this bit here is just algebraic manipulation of this equation. So now what we want to do is we want to get this equation worked around so that it looks like a quadratic equation, because once we have a quadratic equation, we can think of it as a position time function that we can differentiate. So let's just remind ourselves here that a quadratic equation looks like ax squared plus bx plus c equals 0. And so what I'm going to do is I'm going to take each of these pieces of this kinematic equation for position time and equate it or make it correspond to the parts of this quadratic equation. So you can see in this original form of it up here, I'm going to have delta y correspond to c, and I also want you to notice, let me take a red marker and show this here. What's corresponding to x is the t. So we might say this equation is quadratic in time, and we'll get to that in a minute, but let's just keep writing this out here. So v initial t corresponds to this plus bx term. So plus v initial t, and then plus c is plus delta y, and then the squared term or the quadratic term is the 1/2 at squared, and we'll go ahead and write equals 0. So what this means then is that 1/2 a really corresponds to the a coefficient in the quadratic function up here. So 1/2 a corresponds to a. It's not the same as acceleration, it's this a term in the quadratic expression. V initial corresponds to b, and then the change in height or the displacement corresponds to c. Let's now rewrite this as a quadratic expression using this format here. And so we'll write delta y plus v initial t plus 1/2 at squared equals the position as a function of time. And now let's remind ourselves that the derivative of position with respect to time equals velocity with respect to time. So position's derivative is equal to the function's velocity. It's equal to velocity.